Hi everyone, welcome to this presentation entitled Single Stage versus Integrated LED Drivers, a Comparison. This is a paper that was presented at this conference IS Annual Meeting 2024. The authors of this paper are myself, J. Marcos Alonso from the University of Oviedo, David Gasio from Norma Group, Girgis Abdelmessi from the University of Burgos, Spain, Ignacio Alvarez also from the University of Burgos, and Gigi Wang from Harbin Institute of Technology. This is the outline of this presentation. We have first the introduction. We will also introduce then the LED lamp. We will talk about the single stage flyback based LED driver and then about the integrated buck boost flyback based LED driver. We will see the laboratory implementations. We will present the experimental results and discussion, and finally the conclusions. So the idea of this work is something that we wanted to do is the comparison of the operation and characteristics of a single stage flyback based LED driver and an integrated buck boost flyback based LED driver. So here we have the drawing of the single stage flyback based converter. We can see that it's very simple. Also we have a few elements in the converter, so the efficiency is going to be high. This is a converter suitable for any kind of LED lamp, so we don't need to have a specific lamp for the converter because we have the coupled inductor to adapt the input voltage and the output voltage. It can provide isolation, but the main issue of this converter is the high value of the output capacitance because we know that we have to balance the instantaneous input power and the DC output power that we have at the output at the LED lamp. So usually because of this high capacitance we need an electrolytic capacitor at the output in order to have this very high value of capacitance in a small volume. And also another issue is that due to this very high capacitance, the dynamics of this converter is extremely slow. The bandwidth is something like a few hertz. So for some applications, this can be an issue because, for example, if we want to implement PWM dimming at the output, then we have to tackle with this very slow dynamics. So the frequency at which we can perform the PWM dimming can be too low. So the other possibility is the integrated buck boost flyback converter, in which we have a buck boost here at the input and a flyback converter at the output. We have seen this in previous videos. Of course, integrated stages are more complex. They have also lower efficiency because we have more elements. We have the input inductor, the coupled inductors, more diodes and so on, but it has same characteristics as the single stage converter. It is suitable for any LED lamp. It provides isolation, and the advantage is that we are going to require very low value of capacitances in the converter, so we can use field capacitors in this converter, so we can increase the reliability, the lifetime at the end of our LED driver, and also we can provide fast dynamics. So this is the LED lamp that we have used in this work. Is an LED lamp from Norma Group company, and these are the dimensions: 600 millimeters by 600 millimeters. It has 48 LED emitters. The voltage is 72 volts and 0.45 amperes, so the nominal power is around 32 watts. Luminous flux 4320 lumens, and color temperature 3000 Kelvin. So in order to do the design of the converters, we need to first characterize our LED lamp. So this is the behavior of this lamp. Here we have the current through the lamp in amperes, and here the voltage across the lamp in volts. So we obtain several points at the laboratory. These are these red squares. So the model is the dashed blue line. And from this we can get the threshold voltage, 63.7 volts, and the dynamic resistance or the series resistance of our LED lamp, which in this case is 16 ohms. So this is the model that we have for this lamp, and then we can use this lamp to design the converters. Let's see how to do this in the next slides. So this slide summarizes the design of the single stage flyback based LED driver. As we know, we have approximately after the filtering at the input, we are going to have a sinusoidal current at the input and in phase with the input voltage, and this is the instantaneous power that we have at the input. So we need this capacitor to filter and to get a DC average current at the output. So here are the main equations to do the design. This is the equivalent input resistance of the converter, the value of the output capacitance depending on the ripple that we want through the LED lamp. This is the maximum duty cycle for operating in discontinuous conduction mode. So this is an important parameter. We cannot operate with a duty cycle higher than this value because we will enter the continuous conduction mode and then we are going to distort the input current, so we can not satisfy the standard of the harmonic injection into the grid. So this is the turn ratio, and in the paper it is explained how to do the complete design. So here are the values that we have at the end, and this is the output capacitance that we need, which is quite high. It's like 1.3 millifarads. So this is the capacitance that we need here in this case to have the current ripple that we want for this LED driver. So we first tested everything by simulation. So this is a simulation using LTSpice. These files are going to be available from the GitHub site of this channel, so you can download them and test them by yourself. So this is the implementation, including the EMI filter. So here we can see the line voltage. The line current is perfectly sinusoidal and in phase with the line input. This is the output voltage, so we can see that is a DC value of around 72 volts plus 1 volt peak to peak. And then this is the current through the lamp, so it's around 0.5 amperes and 70 milliamperes peak to peak current ripple. And then we have the integrated buck-boost-flyback based LED driver. This is a little bit more complicated to do the design, but again, everything is explained in the paper. So this is the equivalent input resistance of the buck-boost converter. So this is here at this input. This is the value of the bus capacitance, the value of this capacitor, depending on the ripple that we want to get across it. We usually call this as the bus voltage. This is the maximum duty cycle again for DCM operation. We are operating both inductors, the input inductor and also the coupled inductor in discontinuous conduction mode. And another important parameter is what we call the ripple transformation ratio, which is the ratio between the peak-to-peak voltage ripple here and the output, this factor here, over the peak-to-peak ripple voltage at the bus voltage. So this is the factor that we have, and with all these equations we can do the design and finally get the different values. So we can see that the capacitances that we need now, they are very much smaller, only 3 microfarads for the output capacitor here and 11.6 microfarads for the buck-boost capacitor here at the bus and voltage. So yeah, they are one order of magnitude below the design of the single stage flyback based converter, which was around 1.3 millifarads. So again, we did a simulation in LTSpice. So this is the complete circuit, including the EMI filter at the input. This is the stage corresponding to the buck-boost converter, and here we have the flyback converter. So this is the line voltage, the line current, so again is sinusoidal and in phase with the input voltage. We have a little bit more of ripple superposed to the line current, and this is due to the operation of both stages, so we have more ripple in general. In the waveforms, we can see also this in the output voltage. We have the DC output voltage of around 72 volts with some high frequency ripple superposed to it. And then this is the current at the output through the LED lamp. So again, it's like 0.5 amperes and 70 milliamperes peak to peak. So everything is okay. So now we can go to the laboratory and do the implementations to test the experimental operation of these LED drivers. And these are the laboratory implementations. And this is the single stage flyback based LED driver. So this is the inductor. We have used two electrolytic capacitors here in parallel to implement the output capacitor. This is another field capacitor, a small capacitor to do filtering at high frequency. The rectifier, this is the switch. We are not showing here the control circuit. It was implemented using a 3524 PWM modulator and an optocoupler EF&D 3180. So it's very simple control circuitry. So here everything is very simple, but the problem is that the output capacitance is very big in value. So we need to implement this capacitance using electrolytic technology. And here on the right, we have the integrated buck-boost-flyback based LED driver. And this is fully integrated in the sense that we have integrated both magnetics, the buck-boost magnetic here, and the coupled inductor corresponding to the flyback on this other arm here. So we have used the magnetic integration technique in this converter, so we only have to use one magnetics. So this is really interesting because one of the disadvantages of the integrated converters is that we need more elements. So if we implement the magnetics in this way, at the end is something that having the same, almost the same components, just one magnetic, one switch, and several diodes and capacitors and so on. But the difference is that now we need only 15 microfarads and 3 microfarads for the total capacitances of the converter. So this is the bus voltage capacitance, and this is the output capacitance. And they are implemented using film technology, so the lifetime of this converter can be very high, can get maybe 100,000 hours. So let's see now some experimental waveforms. This is the single stage converter, and here we have the line voltage and current. So this is the voltage in yellow, and here we have the current at the input in green. So we can see that the power factor is very high, almost nearly 1, and we can satisfy the harmonic injection standard very easily. And here is the integrated buck-boost flyback based LED driver. So again, we have the voltage in green and the current in yellow. So we can see a more high frequency ripple due to the operation of the converter itself, but in general we can satisfy the harmonic injection standard and also the EMI standards using well-designed EMI filtering. More experimental results here. These are the switch waveforms. So for the single stage converter, this is the voltage, and these are the pulses that we are applying to the gate of the switch. So this is 200 volt peak to peak for this waveform. So this value here is nearly like something like maybe 380 volts, 400 volts, but we have this peak due to the operation of the flyback converter that is unavoidable. We can use a snubber or something to limit the value. In this case, we even didn't use any snubber, so we are handling this directly with the switch because the leakage inductance of the coupled inductors were quite small. So this peak can be something below 600 volts, maybe 550 volts or something like that. And here we have the same waveforms corresponding to the integrated buck-boost-flyback converter. So they are completely different because we have the interaction, a little of interaction between on both stages. But at the end, the peak value that we need for the transistor is nearly the same in both situations. So there is not much disadvantage in using the integrated technology in terms of the voltage rating of the transistor. Here we have more waveforms corresponding to the switch. Again, the voltage across the switch, but now the current through the switch. So this is the triangular waveform, and we can see the DCM operation of the converter. So it's the current that is entering here in the converter. And this is for the integrated converter. So we can see that the waveforms are nearly the same. The only difference is that the peak current here is much higher. This is 4 amperes per division compared to 2 amperes per division here. And the reason, of course, is that this switch, in the case of integrated converter, has to handle both the currents of the input stage and also the current of the output stage going this way. So this switch is handling nearly double the current that we have in the single stage flyback converter due to the operation of at the end of two stages in cascade. And this is one of the reasons that at the end we are going to have lower efficiency in the integrated converter because we have the switch handling more current and we have at the end two magnetic components. And these are the waveforms and the output. So this is the output voltage, the voltage here across the lamp for the single stage flyback converter. This is the current through the lamp. So we can see that the ripple is very small and is satisfying the ripple that was required for this design in order to not have any harmful effect for the user and so on. Everything is explained in the paper. And this is the picture corresponding to the waveforms, the same waveforms for the integrated converter. So this is the voltage and the current, so they are nearly the same with pretty much the same ripple, but we have more high frequency noise due to the operation and due to the interaction of both stages. But in any case, this is okay. So the operation of the LED lamp is nearly the same in both converters. And here we have the efficiency of both converters. The red line corresponds to the single stage flyback converter, and the blue line is the efficiency of the integrated LED driver. So we can see that the efficiency, of course, of the single stage is much higher, is reaching nearly 95% here at this peak value, and here at full power at the output this is something like 80.5%, and this is something like 90%. So the efficiency is higher, but of course we have other disadvantages in the single stage LED driver as we have seen. So finally, summary and conclusions. Here we have a more detailed comparison in terms of input power factor. So they are very good, both of them. The distortion at the input is a little bit lower in the case of the single stage converter, but in any case is small in both of them. The total filter capacitance is much smaller in the case of the integrated and buck-boost converter, so this is an important advantage. We can use film capacitors very easily. The current ripple is the same, galvanic is isolation. The reliability, of course, is going to be much higher for the integrated converter because we can use film capacitor. The control circuit is exactly the same because we have to drive only one switch and do the current control in closed loop and regulation of the current, so it's not complicated. The efficiency is high, quite high for the single stage converter and not so high for the integrated converter, something like 81%. the volume of the converter is smaller in the case of the single stage converter, but of course this is also considering that we are going to use electrolytic capacitors, because if we use film capacitors for the same value is going to be much higher. So in the case of the integrated converter, we can use film capacitors and then integrate also both inductor and the coupled inductor of the flyback converter, and we have a medium size converter, so it's not that bad. The volume of both magnetics at the end is not so different. This is something like 10,000 cubic millimeters compared with 13,000 cubic millimeters, so at the end it's not so big difference. Analog dimming can be easily implemented in both converters, but PWM dimming is more difficult to be implemented in the single stage converter due to this very high value of the output capacitance. So the dynamic is going to be slower because of the high output capacitance, so it's going to be much easier to be done using the integrated converter. The cost, of course, is going to be lower in the case of the single stage converter because we need less components, while in the case of the integrated converter it's a little bit more expensive. So at the end, similar characteristics in terms of power factor, harmonic distortion, and lamp current ripple. The main advantage of the integrated solution is its ability to drastically reduce the amount of capacitance required to implement the converter, but we have of course, the disadvantage of higher cost and lower efficiency. But we have also to consider that we are going to have a much longer lifetime for the integrated converter. So even though if we have a lower efficiency, we can compensate this in terms of cost by having a longer lifetime. Well, this concludes this presentation. Today I want to show you my beautiful city, Gijón, in the north of Spain. And please let me know if you have any comment or question through the comment section of this video. I hope that this presentation is useful for you. Thank you for watching, and I hope to see you in the next video. Goodbye now.